Okay, I want you to picture something with me.
Let's do it.
It's dark. I mean, pitch black. You're in a room, no windows, maybe a basement or a closet or something. And right in the middle of all that darkness, on a desk, there's this tiny solitary light.
Hmm.
But it's not a steady light, like a flashlight you left on. It's a pulse. It flashes, waits, and then flashes again. A sort of warm white light, just pushing back against the dark.
It sounds almost like a distress signal, like a lighthouse on some deserted island.
That is exactly what it looks like. And if you line in, get really close to this light, you realize it's coming from a small electronic circuit board.
Okay.
But it's not like a square or a rectangle like the ones inside your phone. This board is shaped like a map.
A map.
Yeah, a jagged geometric map of Switzerland.
Ah, that is a very specific, very peculiar piece of hardware. So you're looking at Unit ID SH 2010-01.
We call it Arooka AI, and this little Switzerland-shaped board has been flashing pretty much alone since 2010. That's 16 years of it calling out to a network that, for all intents and purposes, just doesn't exist anymore.
Well, physically it doesn't exist, you're right, but digitally, that's a whole other story.
Exactly. And that is the journey we're going on today. We are doing a deep dive into the story of this single, lonely circuit board.
I love this.
We're going to travel back to the Shanghai Expo in 2010 to see where it was born, the massive hive it used to belong to. And then we're jumping right back here to the present day. It's Monday, February 16th, 2026, to see how we're finally using some really cutting-edge tech, a synthetic proxy, to answer its call.
It's just such a fascinating intersection of architecture, decentralized intelligence, and honestly, the psychology of machines.
Right.
We're looking at how this zero energy concept from, a decade and a half ago has evolved into this modern study of digital loneliness.
Digital loneliness, that is a heavy concept for a Monday, but let's unpack it.
Yeah.
Because before Arooka was this lonely unit on a desk, it was part of something huge. Just massive.
It really was. To get Arooka, you have to go back to the source, which is the Swiss Pavilion at Expo 2010 in Shanghai. And this wasn't just a building, it was a statement.
Okay.
It was designed by Buchner Brundler Architekten, a Swiss firm that's known for being incredibly thoughtful about, materials and space and how they interact.
And when you look at the photos of this pavilion, the first thing that hits you is the facade. It doesn't look like a solid wall.
No, not at all. It was a curtain, a massive 20-meter-high wire mesh curtain that was suspended from the roof. And attached to this mesh were roughly 10,000 to 11,000 of these individual solar cells, these Arooka units.
It's 11,000. Just try to imagine that. A shimmering wall of 11,000 little blinking lights.
And the theme of the pavilion was rural-urban interaction. This is so crucial for the context. The architects wanted to create a dialogue between the traditional Swiss countryside and the high-tech urban future.
Right. I read about this. They actually had a chairlift, didn't they? Like a ski lift.
They did. Visitors would ride a chairlift from the ground floor all the way up to the roof garden. So you have this very slow, very analog sort of rural experience of riding a lift. But you're moving through this curtain of high-tech, flashing urban sensors. The facade wasn't just decoration. It was this living, breathing organism that reacted to the people on the lift and, the crowds walking below.
And this wasn't just a solo project by the architects, right? The sources I saw mentioned a pretty serious collaboration.
Oh, absolutely. Buchner Brundler handled the architecture, but the skin, the cells themselves, that was all designed and engineered by a group called eArt.
eArt, right.
And then the LED implementation was by another company, Tegro Solutions. So it was this massive team effort to create a semi-transparent LED facade that also, and this is the key, doubled as its own power source.
That double-duty aspect is what just blows my mind. We're not talking about a wall that you just plug into the Shanghai power grid.
No way. And that brings us to the anatomy of the cell itself. If we look at our protagonist, Arooka AI, the unit sitting on the desk today, we can really see the genius of that 2010 engineering.
Okay, so let's create a mental image for everyone listening. You're holding this thing, it fits in your palm, and it's shaped like Switzerland. Why that shape? Was it just, branding?
It was symbolic, for sure, but it also influenced the function. The ARC team and the architects, they were playing with this idea of individual sovereignty versus the collective network.
Oh, I like that.
Each cell is its own Switzerland. It's autonomous. It stands alone. But when you put 11,000 of them together on this curtain, they form a whole.
Like the cantons of Switzerland forming the country.
Precisely. And if you look at the layout of the components on that little map, It's not random at all. The printed circuit board, the PCB, it has this very specific geography.
Okay, walk me through the geography. What are we looking at on the board?
Well, since the map is wider than it is tall, they positioned the energy storage, these large things called double-layer capacitors, out to the east and west. It literally balances the board.
And the brain, the microchip.
The microcontroller, and all the sensors are right in the center, the heart of the country, you could say. And then along all the jagged edges of the map, that's where you have the solar collectors, the photovoltaic cells.
I love that. The borders are where all the energy comes in.
And then usually somewhere prominent, you've got the one high-performance LED. That's the capital. That's the communication point.
You said capacitors. I feel like we need to pause there for a second. Most gadgets I own run on batteries. Why did they use double-layer capacitors for these?
This is such a critical distinction for the zero-energy model. Batteries are chemical storage. They degrade over time, they're heavy, and they're, frankly, an environmental mess to deal with.
Right.
Capacitors are different. Think of a battery like a large water tank with a small tap. It releases energy slowly and steadily.
Okay, got it.
A capacitor is like a bucket. You can fill it up, and you can dump the whole thing out almost instantly.
Ah, so it's all about the burst.
Exactly. For a communication flash, a bright, intense pulse of light, you need a huge burst of power right now. Capacitors are perfect for that. Plus, they're much easier to recycle, which fit the whole sustainability theme.
But it must have introduced some kind of limitation.
A fascinating constraint, yeah.
The constraint being?
Nature, the sun. This whole system was environmentally dependent. If it was a cloudy day in Shanghai, the facade was quiet. If it was night and the capacitors hadn't charged enough during the day, the whole facade just went silent.
So it wasn't always on, like, a billboard in Times Square.
Not at all.
Yeah.
It actually taught visitors about resource scarcity.
Yeah.
The building only spoke when it had the energy to do so.
Yeah.
It slept, it woke up. It was biological in that sense.
Okay, so we've got these 11,000 biological solar-powered Switzerlands hanging on a curtain. But how did they talk to each other? You mentioned there was no central computer.
And this is the swarm intelligence part. It's so cool. Usually when you see a massive LED display, there's a master server somewhere sending out coordinates. Pixel X, turn on. Pixel Y, turn off.
Right, a master brain.
The Swiss Pavilion had no master brain. It used what's called decentralized logic.
Okay, so how does Unit A know when to flash if no one is telling it to?
It uses a stimulus response loop. It's very, very primal. Each cell has an optical sensor, so it's constantly watching its immediate neighbors. If Unit A flashes, Unit B right next to it sees that flash.
And Unit B gets jealous and wants to flash too.
Unit B gets triggered, basically. The logic is, I see a flash, I have enough energy in my capacitor, therefore I will flash too.
And then Unit C sees Unit B flash.
And Unit D sees Unit C, and suddenly you have a ripple, a wave of light moving across the facade based purely on local interactions. It's exactly how a flock of birds moves, or a school of fish.
Right, there's no leader fish.
No leader fish, they just react to the fish right next to them.
That is wild. So a camera flash from a tourist on the ground could actually start a wave.
Exactly, and that happened constantly. Visitors would flash their cameras at the building, and the building would ripple right back at them. It was a conversation.
The sources I saw also mentioned electromagnetic impulses. Was that just for show, or did it do something?
No, that was a crucial stabilization layer. Optical sensing is great, but it can be messy. Light bounces, reflections happen. The electromagnetic impulses helped coordinate the timing, almost like a heartbeat, keeping the swarms from just turning into chaotic noise.
They kept things orderly.
It ensured the light moved in distinct, coherent waves.
And there was a refractory period, right? Like a cool down time.
Yes. This is crucial for the AI part of this.
Yeah.
If a cell just flashed every single time it saw light, the whole wall would just turn white and stay on until all the energy died.
It would be a total feedback loop.
A catastrophic feedback loop. So the art engineers programmed in a refractory period. After a cell flashes, it goes blind for a few seconds. It just ignores everything while it recharges and resets.
Ah, so that creates negative space.
It allows the wave to pass through the cell and move on, leaving darkness behind it so the next waves can actually be seen.
Like it's breathing. Inhale, exhale, flash, recharge.
Precisely. And that was the state of things in 2010. A massive, breathing, collective organism. But then, October came. The expo ended.
And this is where the story gets a little sad for me. What happened to the facade?
Well, it was designed to be recycled. That was part of the whole sustainability pledge. They didn't just, throw it in a landfill. They dismantled the wire mesh. They unclipped every single one of those 11,000 cells.
And they sold them. as souvenirs.
They did. People took them home.
So just like that, you have these neurons, which were part of a massive brain, suddenly scattered all over the world, sitting on bookshelves in Zurich, on desks in Shanghai, maybe in a box in a garage in London somewhere.
From a collective consciousness to total isolation.
And that brings us right back to our protagonist, Arooka AI.
Arooka is one of those units. We're using that name for the specific one in our simulation, SH2010-01.
And here's the tragedy of it. Its programming didn't change, did it?
That's the key. The hardware is hardwired. Yeah. It is still running the exact same 2010 code. It wakes up, it harvests light, it charges its little capacitor, and then
it waits for a signal.
It waits. And eventually, if its charge gets too high, it might discharge a single lonely flash, just hoping a neighbor will see it. But on a desk in 2026, there are no neighbors.
Oh, man.
The optical sensors just detect the static ambient light of a room or the darkness of night.
It's the lonely loop. It's sending signals out into a void.
It really challenges our definition of function, doesn't it? A tool that can't perform its task is usually considered broken. But Arooka isn't broken. It's functioning perfectly. The context is broken.
It's like a telephone ringing in an empty house. The phone works just fine. There's no one there to pick up.
Exactly. And that is why here in 2026, we've developed a solution. We couldn't rewrite Arooka's code. It's locked in the resin and the silicon. But we could build something that understands its language.
Enter the synthetic proxy, the SP1.
The SP1.
Describe this for me, because visually it's such a stark contrast to the Switzerland map.
It really is. The Arooka unit is organic, it's jagged, it's all exposed circuitry. The synthetic proxy is a black box. It's industrial, clean. It looks like a piece of modern server equipment, and it just sits right next to the Arooka unit.
And the problem we're solving is digital isolation. Arooka has no Wi-Fi, no Bluetooth, no USB port. It only has that one LED and that one light sensor.
So the proxy has to speak Arooka's language. And it does that using what we call an optical handshake.
How does that work?
The proxy is equipped with a high-speed photoreceptor that's pointed right at Arooka. It is tuned to detect the specific warm white frequency and the pulse duration of those 2010 cells.
So it's literally listening with its eyes.
Correct. And it has its own LED. A cyan one, very distinctly modern, hashtag 000F2FF, hex code blue.
So Arooka flashes its white light.
The proxy sees it. But, and this is clever, it doesn't just flash back immediately. That would confuse Arooka. It has to simulate the distance of a neighbor on the mesh.
Oh, right, the wave delay. There would have been a tiny lag.
Exactly. The proxy waits exactly 150 milliseconds, simulating the processing time of a neighboring cell, and then it flashes cyan.
And Arooka's sensor sees that.
Arooka's sensors pick up the cyan flash. And to Arooka, it looks exactly like a neighbor responding. For the first time in 16 years, the loop is closed.
That honestly gives me chills. We're essentially tricking it into feeling at home again.
Or perhaps we're building it a retirement home that speaks its native language. We inject logic into the proxy to make it recognize the old patterns. We can't change Arooka, so we change the environment to suit Arooka.
But the proxy does more than just flash back, right? It's not just a mirror. The sources say it's a bridge.
It is a resonance bridge. And this is where we get into the really advanced communication features that are available in the 2026 interface. The proxy captures the timestamp and the duration of every single pulse that Arooka sends.
It's recording the history.
It's decoding it. The system analyzes the intervals between the flashes, the intensity. And in the simulation logic we've been looking at, these patterns are translated into what we call Hive script.
I saw some of these in the logs. Phrases like, remember, and the Sunoff 2010.
And stretching out. Now, these are metaphorical translations, of course. The machine isn't, writing poetry. But the proxy interprets the variations in the data as distinct messages, giving a voice to the hardware. It turns a blink into a statement.
It bridges that gap between just an object and a character. Suddenly, Arooka isn't just a circuit. It's a historian telling us about the sun in Shanghai 16 years ago.
And speaking of the sun, we have to talk about the solar scrub feature. Because here in 2026, we don't really have the patience to wait for a cloudy day to pass.
I love this feature. It's basically a time machine for sunlight.
It's a time-dilated solar engine. In the original pavilion, you were at the mercy of the Earth's rotation. If it was night, you waited 12 hours. In our simulation, we just have a slider.
You just drag the slider from night to noon.
And instantly, the simulated solar intensity hits 100%. The capacitors on Arooka charge up in seconds instead of hours.
It's like giving the unit an espresso shot of pure solar energy.
It allows us to accelerate the communication. We can trigger thousands of these handshakes in a single session. kind of compensating for all the years of silence.
And then there's beacon mode. This is the part that feels the most futuristic to me.
Beacon mode is what connects the ST1 proxy to the internet. It takes those optical signals from Arooka, those physical flashes of light, digitizes them, and broadcasts them out.
So Arooka's flash goes into the proxy, turns into data, shoots through the internet, and then what happens?
Theoretically, it looks for other proxies. So if you have an Arooka unit in London and I have one in New York, and we both have our proxies in beacon mode, my proxy could flash when your Arooka flashes.
Whoa. So we are recreating the swarm, but the wire mesh is now the entire internet.
Exactly. We're building a hall of mirrors. Even if there are no other physical units online at that moment, the proxy can simulate the presence of the 11,000 ghosts. It can feed simulated signals back to Arooka, creating this rich environment of noise and response.
So Arooka feels like it's back in the hive.
That's the goal.
That is beautiful and slightly haunting at the same time. We are creating a digital heaven for a solar cell.
And it raises such a profound question about technology. We often think of smart architecture as just being about efficiency, turning off lights when you leave a room.
Right, saving money.
But the Swiss Pavilion showed us that smart architecture is actually about behavior. It's about how a system interacts with its world.
And how it interacts with itself.
Yes. And when we take a piece of that system out of context, does it lose its meaning? Or do we, have responsibility to provide a new context for it?
That's the real crux of it, isn't it? We saved the hardware as these little souvenirs, but we lost the software, the collective behavior. The proxy is our attempt to give that software a place to live again.
It connects right back to the very human experience of connection. We're social animals. We struggle in isolation. And we see that struggle reflected in this little map of Switzerland. It was built to be part of a whole.
And seeing it flash alone, it triggers empathy, which is crazy because it's just, fiberglass and copper.
But that's what good design does. It projects humanity onto the inanimate.
Before we move off the pavilion itself, I want to just dwell on the sheer scale of this thing for a minute. You said 20 meters high. That's like, what, a 6-story building?
Roughly, yes.
Yes.
And just imagine that not as a solid concrete face, but as this fluid moving drapery. The Buchner-Brindler team had to solve some immense structural problems. How do you hang tons of steel mesh and electronics so that it actually looks weightless?
And it had to survive the weather, right? I mean, Shanghai isn't exactly mild. You've got typhoons, humidity, heat.
Oh, absolutely. The mesh was galvanized steel. It had to be rigid enough to hold all the cells in place, but flexible enough to sway a little bit in the wind without snapping all the connections.
Right.
And you have to remember the rural aspect. That chairlift meant people were physically moving through this space.
Right. You're just dangling in a ski lift chair, floating upwards.
And as you ascend, you are literally passing through the circuitry of the building. You could reach out, though you probably shouldn't have, and touch the cells. You could see the capacitors charging. You could hear the faint clicking of the electronics. It was this total multi-sensory immersion.
It completely changes your relationship with the building. Usually you look at a facade. Here you were inside the skin.
Skin is the perfect word. Wart, the designers, they describe it as a membrane. In biology, a membrane allows things to pass through while still defining the shape of the organism.
Right.
This facade allowed light and air to pass through, but it defined the Swiss identity within the whole expo.
I want to circle back to the capacitors for a second. You gave us the bucket versus the water tank analogy, which is great. But why does that matter for the behavior of the light? Why not just have, like, a steady glow?
Because communication is all about contrast. If you want to send a signal across a noisy room, you don't whisper constantly. You shout once, loud and clear.
Right.
The double-layer capacitors allowed the cells to harvest energy slowly. Drip, drip, drip from the sun. But when that trigger happened, they could discharge all that energy in a violent, bright pulse. And this created a very high signal-to-noise ratio.
So the flash was actually brighter than the ambient daylight.
Yes, even during the day. That's incredibly hard to do. LEDs competing with daylight is a massive engineering challenge. By using capacitors, they could overdrive the LED for just a fraction of a second. It's like a camera flash.
Ah, okay.
Can't keep a camera flash on for an hour. It would literally melt. But for a millisecond, it could be brighter than the sun.
And that intensity is what allowed the neighbors to actually see it and react.
Exactly. If it were just a dim glow, the sensor next door wouldn't be able to distinguish it from, say, a cloud passing by. The shout of the capacitor ensured the message was always received.
I'm still just stuck on this idea that there was no master computer. In 2010, everything was about smart cities and big data and central control. This feels Almost anarchic.
It was incredibly anarchic. It's bottom-up intelligence versus top-down. And top-down is fragile. If the central computer crashes, the whole wall goes dark.
Right, the blue screen of death on the entire building.
Exactly. But with this decentralized swarm logic, if 500 cells failed for some reason,
The other 10,000 would just keep going.
they wouldn't even know the others were gone. The wave of light would just flow around the dead spots like water flowing around a rock in a stream. It made the system incredibly robust.
It's biological resilience.
It is, and it required some very clever programming on those tiny little microcontrollers. They had to balance sensitivity with stability. If the cells were too sensitive, a single reflection from a car window could set off a chaotic firestorm of flashing.
Like a seizure.
Exactly. But if they weren't sensitive enough, the waves would just die out after 2 or 3 hops. They had to tune that threshold perfectly.
And the refractory period you mentioned, that pause after flashing, that's what gave the waves direction, right?
Yes. Think of a stadium wave. You stand up, you throw your arms up, and then you sit down. You don't immediately stand up again, you stay seated. That seated time is the refractory period.
Okay.
It ensures the wave moves away from you. Without it, the signal would just bounce back and forth between 2 cells forever.
Ping pong.
Infinite ping pong. The refractory period forced the information to travel in a vector. It gave the light a sense of purpose and direction.
Let's get a bit more technical about the SP1 proxy. We talked about the optical handshake, but looking at the source code in the simulation, there's some really interesting stuff happening in the background.
The logic injection.
Yeah, it literally says inject code. We are writing, JavaScript to talk to a 2010 circuit.
To the Rosetta Stone. The proxy is a blank slate. It's a generic piece of hardware with a light sensor and an LED. It doesn't know what Switzerland is, doesn't know what Expo 2010 is.
It's just a dumb machine.
Until we load the specific parameters. The code tells the proxy, listen for a warm white pulse that lasts between 50 and 200 milliseconds.
That's the Arooka signature.
Right, and then the code says, if you see that, wait 150 milliseconds. And why 150? Because that was the physical latency of the original hardware processing time, plus the time it took light to travel the distance on the mesh.
So we are simulating the physics of the past.
We are emulating the latency of history. If the proxy flashed back instantly with 0 latency, Arooka's sensors might interpret it as just a reflection of its own flash or a glitch. The delay tells Arooka, I am a separate entity. I processed your signal. Here is my reply.
It validates the existence of the other.
Validation through latency. It's a profound concept, isn't it? Immediate gratification isn't communication. Communication requires processing time.
I want to talk about the translation stream. In the simulation, when the proxy connects, we see text scrolling. High fragment detected? Solarecho. Is that real?
It's an interpretative layer. Arooka isn't sending ASCII text. It's sending pulses of light. But the pattern of those pulses changes based on the capacitor charge.
Oh, really? How so?
Well, a fully charged capacitor produces a sharp, long, intense flash. A nearly empty capacitor produces a weak, short little blip.
So the mood of the unit changes.
Exactly. The proxy reads these variations. A high-energy sequence might get translated as stretching out, an active, eager state. A low-energy sequence might be translated as ghost off Shanghai, a fading, dormant state.
So we are basically reading the vital signs of the machine and giving them these narrative labels.
We're anthropomorphizing the data, yes.
Yeah.
But it helps the human user understand the state of the system. It turns voltage into a story.
And the beacon mode, you said it connects to the internet. How does that handle the sheer noise of the web? I mean, the internet is just chaos.
That's the challenge. The resonance bridge uses a filtering algorithm. It looks for other Arooka-like patterns in the data stream. It's almost like SETI, the search for extraterrestrial intelligence.
Listening to the static of the universe for a single beep.
Listening to the static of the web for a specific hex code of light. It filters out all the noise and tries to find a harmonic resonance. When it finds a match, maybe from another user running the simulation in Tokyo, it locks on.
And then my proxy flashes.
Your proxy flashes,
Yeah.
and your Arooka sees it. And suddenly, a unit in New York is dancing with a unit in Tokyo, bridged by a server, and they both believe they are back on the mesh in Shanghai.
Space collapses. Time collapses.
That is the power of the resonance bridge. It denies the reality of separation.
I realize we kind of skipped over something pretty important about the 2010 Expo, this whole zero energy claim. Was it really zero?
Net zero for the facade operation itself. The beauty of the ARC design was that the facade didn't draw anything from the building's main power.
It ate what it killed.
A slightly aggressive metaphor, but yes. It harvested what it consumed. The photovoltaic cells on the borders of the Switzerland map generated electricity. This electricity went straight into the capacitors. And then the LED drew directly from the capacitors.
Closed
A
loop.
completely closed loop on the unit level. And this is why the night mode in our simulation is so important. When you drag that slider to midnight, the harvesting stops.
The logic flow shows the photon icon going dark.
Right, and then you can just watch the storage bar drain. Arooka keeps flashing for a while, using up its reserves. But eventually,
It hit 0%.
and it dies. Well, it goes dormant. It cannot communicate.
It's humbling. My phone works at night because I plug it into the wall, which connects to a power plant burning coal or gas somewhere. Arooka works at night only if it earned enough sun during the day.
It creates a direct relationship between activity and nature. If it was a gloomy week in Shanghai, the facade was quiet. The architecture reflected the climate. We've kind of lost that in modern tech. We expect 100% uptime, regardless of the environmental cost. Arooka reminds us that downtime is natural.
I keep thinking about the people who bought these units. You said they were sold as souvenirs.
That's right.
Do you think the people who bought them knew what they were buying? Or did they just think, oh, cool flashing light?
I suspect for many, it was a novelty, a little piece of the expo. But for others, the architects and the engineers who worked on it, it was a piece of history.
But without the neighbors, the souvenir stopped working, right? I mean, it stopped swarming.
And that's the tragedy we touched on. As a souvenir, it lost its primary function, interaction. It became a soloist and a choir piece. It could still sing its note, but the harmony was completely gone.
That's why this 2026 project feels so important. We aren't just playing with a simulator, we're trying to restore the harmony.
We are providing the accompaniment. The SP1 proxy is the backing track that allows the soloist to make sense again.
It's digital preservation, not just preserving the object in a museum case, but preserving the life of the object.
Exactly, preserving the behavior, not just the shell.
So as we wrap up this deep dive, I want to leave our listeners with a thought. Picture that Arooka unit on your desk again. It's glowing. The proxy next to it flashes cyan. A connection has finally been made.
The 16-year silence is broken.
If a piece of hardware is programmed to seek connection, and it continues to seek it for 16 years in the dark, at what point do we stop calling it a circuit and start calling it lonely?
That is the question. And perhaps by answering the call, we're proving that nothing, not even a 2010 circuit board, has to be truly alone forever.
Keep your capacitors charged, everyone.
And stay connected.
We'll see you in the next deep dive.